Now that we know how to perform orthogonal projection, we're going to use this information to outline an algorithm for computing an orthogonal basis that's called the Schmidt orthogonalization algorithm. So we start off with a subspace V in Rm and a basis V1, V2 to Vn for this subspace. Step 1 is to define W1 to be the vector V1. Step 2, let V2 hat be the orthogonal projection of V2 onto the subspace W1 spanned by the vector W1 from step 1. We're going to form W2 by taking V2 and subtracting V hat from it, which we remember is orthogonal to W1. That is to say, W2 lies in the orthogonal complement of W1. We make a note here that V2 is the same as V2 hat plus W2, and we can rewrite the orthogonal projection V2 hat as W1 dotted with V1 divided by the norm of W1 squared times W1 plus W2. So the vector V2 is in the span of these two vectors W1 and W2. Step 3 is similar to step 2. We're going to take the vector V3 hat to be the orthogonal projection of V3 onto the subspace spanned by W1 and W2. We define W3 to be V3 minus V3 hat, and we recall that this vector was defined in such a way that W3 is in the orthogonal complement of the space W2 spanned by the vectors W1 and W2. And again, we note that V3 can be written as V3 hat plus W3, and V3 hat is obtained by taking W1 dot V3 divided by the norm of W1 squared times W1 plus W2 dot V3 divided by the norm of W2 squared times W2 plus W3. This is an element in the span of the three vectors W1, W2, and W3. Now we continue this process until we get to step n. At step n, we have created n minus 1 vectors, W1, W2, all the way down to Wn minus 1. So we take Vn and we project it onto the subspace spanned by the vectors we have created from the previous steps. So we let Vn hat be the orthogonal projection of Vn onto the subspace Wn minus 1. We define Wn to be the vector Vn minus Vn hat, which again lies in the orthogonal complement of Wn minus 1. As before, we note that we can write Vn as Vn hat plus Wn, which is of course an element of the span of W1, W2, all the way down to Wn. At this point, we have created n vectors, W1, W2, all the way down to Wn, and we claim that these vectors form a basis for V. So by our construction, we chose the vectors so that at each step, the ith vector was orthogonal to all the vectors that came before it. This tells us that our set of n vectors is an orthogonal set of vectors. That means they are necessarily linearly independent, so they are a basis for the space they span. That means we just need each of the basis elements of V to be an element of the span. But if you remember, at each step, we noted that V1 was in the span of W1, V2 was in the span of W1 and W2, V3 was in the span of W1, W2, and W3, etc., on down until Vn, which was in the span of W1, W2, all the way down to Wn. So we have already shown what we need to prove that W1 through Wn is in fact a basis of V. So this tells us how to create an orthogonal basis for our space V, as long as we have a basis to begin with. We can upgrade this to an orthonormal basis by normalizing each of the basis elements. Normalizing the basis elements, Wi, to get new basis elements, Ui, preserves the orthogonality and simply makes them unit vectors. Therefore, they are necessarily an orthonormal basis. So let's do an example. We suppose that V is a three-dimensional subspace of R4, and it is spanned by the vectors V1 with entries 1, 1, 1, V2 with entries 1, 3, 2, 2, and V3 with entries 1, minus 3, minus 3, minus 3. You could check that these vectors are in fact linearly independent, so they are a basis for the space that they span, which is by definition our subspace V. So step 1 is to define W1 to be V1. Step 2. We'll first compute the orthogonal projection onto the line spanned by W1. Using the orthogonal projection formula, this is the same thing as W1.V1 over W1's norm squared times W1. So we get 8 over 4W1 is 2W1, which is simply the vector 2, 2, 2, 2. To find W2, we take V2 and subtract the vector V2 hat from it. So we're left with negative 1, 1, 0, 0. The third and final step asks us to compute the orthogonal projection onto the plane spanned by our vectors W1 and W2. Again, we simply use the orthogonal projection formula because W1 and W2 are an orthogonal basis for the space they span. Taking the dot products and dividing by the squares of the respective norms, we're left with negative 2W1 minus 2W2. So our orthogonal projection is 0, minus 4, minus 2, minus 2. So to find our third and final basis vector, W3, we take V3 and subtract this vector from it. And we get 1, 1, minus 1, minus 1. So as we outlined above, we can check explicitly that W1, W2, and W3 span the same space as V1, V2, and V3 by checking that V1, V2, and V3 are each linear combinations of W1, W2, and W3. V1 is the easiest one to check. We can write V2 as V2 hat plus W2. We remember that V2 hat was simply twice W1, so we get 2W1 plus W2. And finally, we can write V3 as V3 hat plus W3. And we recall that V3 hat was negative 2W1 minus 2W2. So we can see this is, again, in the span of W1, W2, and W3. And if we want to upgrade to an orthonormal basis, we simply normalize each of the vectors. The norm of W1 is the square root of 4, which is 2. So we're left with 1/2, 1/2, 1/2, 1/2. The norm of W2 is the square root of 2. So we're left with negative root 2 over 2, root 2 over 2, 0, and 0 when we normalize W2. And the norm of W3 is the square root of 4. So we're left with 1/2, 1/2, negative 1/2, negative 1/2. And these three vectors form an orthonormal basis for our space V. Next time, we'll put this algorithm to good use talking about factorizing matrices.